I would like to start with probably the most basic regime that we are going to talk about in machine learning. I would like to start with the setting in which we learn with supervision. And of course, you might have many arguments whether this is a realistic or a valid or a useful scenario. We'll see that there are, of course, many tasks where this scenario is very useful, and we will see in subsequent lectures that we can actually use the same models that we are going to develop in this supervised setting in more general settings, in absence or in the presence of different forms of supervision. Okay, so we'll start with supervised learning. I would like to show you today some elementary notions in machine learning. Again, this is not a theoretical course, but we'll see some basic math, some basic notions behind machine learning. And basically, next week we are going to talk about deep neural networks specifically. So this will justify our purpose of being a deep learning course. Okay. So let's start with some basic notions. I would like first to define what we are going to call an instance space. So basically, instance space is just a way of saying that this is the space from where our data come from. Okay, so basically, data will be points in this space. So let's denote it by X. This calligraphic X, I will, at least for the simple setting that we are going to address in the few following weeks, let's assume that this is a finite dimensional and n-dimensional vector. Okay, so basically this instance space will be just a subset of Rn. Okay, and then we'll see what happens, for example, if the input dimension is not fixed or not known ahead of time, like what we could have in the case of language. We don't know the length of a sentence ahead of time. Okay, I will be denoting points in this space as column vectors, coordinates x1 to xn. Okay, and then I will define another space that I will call label space. So label space will be a set of labels that we attach to instances. Okay, so there we can distinguish between two very similar problems. One of them will be classification. In this case, the label space will be a set of discrete labels. For example, I can have a space in which I have labels like cat, dog, table, desk, chair, and so on. And then I would like to assign for each instance space, for example, an instance space may be a space of images that I'm capturing with a camera, and I would like to assign to each of these instances a label in the label space. For example, whether this is an image of a dog or this is an image of a cat, and so on. Okay, so this is called a classification problem. I would like to assign a class label to my input data point. Okay. In the case we have some continuous label space, I will still call points in this space, I will still call them labels, but the problem becomes a regression problem. Okay, so basically this is the distinction. Again, the mathematical instruments that we are going to develop will be very similar for classification and regression, but the meaning is different. For example, suppose I'm measuring the location of an object, let's say in space, okay, and I would like to develop a model that describes its mechanics. For example, I'm launching a projectile, a bullet, let's say, and I would like to define the laws of physics that govern it. Okay, so you can think, of course, let's take the Galilean model of a quadratic function that basically takes the initial location, the initial velocity, into account the acceleration of free fall, so on, right? This would be some approximation of reality. Maybe we would like to add some friction, some other forces that act on this projectile, and then we'll find a model that fits the data in a better way. Okay, so basically all these models would be maps between the instance space to the label space. Okay, but now the label space is continuous. It's the location of an object, right? So basically in this case we're talking about a regression problem. So basically, as I said, we have some underlying target function, a map between the instance space to the label space. Okay, so for example, in case of images that I would like to classify, in case of visual recognition, I would like to assume that there is some ground truth information that, for example, tells me that this is an image of a dog or this is an image of a cat. Okay, it's quite a reasonable assumption in many scenarios. Same about my physics example. I can have this target function because I know where the object was located, for example. Okay, so this is the target function, and in many situations the target function doesn't exist, or it exists in some noisy form. So suppose my map looks like this. So it's not exactly X mapping to a single point in the label space. I might have some distribution around this point. Basically, I might have some variance. I might label the same image in different ways. It might be ambiguous, right? I might have some modeling noise, right? Basically, there might be different reasons why my target function is something non-deterministic. There might be some stochasticity inherent to the labeling process to this map. Okay, a question, please. Yes, exactly. So, well, I will formulate exactly what is the target, what is the objective of supervised learning. But essentially, I'm going to look for this label function or some stochastic version of it. Okay. So basically, if this noise has zero variance, we are back to the deterministic case, right? And we can formulate this entire setting in a slightly more rigorous or elegant form by using distributions. Okay, so I'm drawing a one-dimensional visualization. Hopefully it is clear. So the horizontal axis is the instance space. I'm drawing it as a one-dimensional space. Of course, in general, this is a high-dimensional space, right? And the label space, again, is the vertical axis. It could be one-dimensional, it could be multi-dimensional. Okay, so in regression problem, for example, when we would like to regress the x, y, z coordinates of a flying object, this would be a three-dimensional space. And basically, what I have is a joint distribution. Joint, it's the instance x and the label y. Okay, so basically, for these couples, for these pairs of instance coupled with label, I have some distribution, right, which lives in this product space. Okay, and I can compute its marginal. So basically, it's marginal here. It's the instance distribution, right? So if I marginalize p x y, if I marginalize it with respect to y, right? Basically, I accumulate all. Basically, I integrate over all that noise around my target function. I will get an instance distribution. Okay. And of course, I can fix a single point, a single instance x, okay? And what I will get is some distribution around its mean, right? So it will have some mean, which is this conditional expectation y given x, okay? And there will be some spread around this mean. If my target function is deterministic, this will be just a singleton distribution. It will be a delta, right? It will be just a number. The conditional distribution will make this conditional variable deterministic. Otherwise, I will have some spread, and this is exactly the noise that we had here. Exactly this distribution. Okay. And of course, we can write the joint distribution as the product of the marginal instance distribution times this conditional distribution of the label given the data. Okay. So you can think of this conditional distribution of this term here as some stochastic version of the target function, right? Basically, I give you the data and you give me the label. Well, the label might be not deterministic, so give me the distribution of this label. Okay? Yes, a question? So the question was, for the sake of the recording, the question was basically, what do we do in reality? Of course, in reality, we can think about this space, but we don't know what happens in it, right? Basically, we need to discover what happens in it. And essentially, in these terms, what we actually have is a finite sample of pairs, instance, and its label. Okay, so basically, we don't have access to that continuous picture that I drew. What we have instead is a finite sample, sampled from that picture. So basically, what we have, let's think in the deterministic setting, what we have is some sample of the instances. So I'm sampling from the marginal distribution px, and let's assume that this sampling is IID. So basically, it is independent, statistically independent. The samples are statistically independent and identically distributed. Okay, so basically, this IID assumption might sometimes or oftentimes be unrealistic, but if we don't assume it, then any analysis will become painful or practically impossible, right? So we'll make this IID assumption, and we'll strive to make it actually to make it true in reality in the way we construct our training set. Okay, it might be very difficult in practice. So if I sample my instances from the instance distribution, these are the points that I'm showing here, I can plug them into the target function, which again, basically I'm measuring it from some real setting. So basically I'm labeling my instances, and as a result I get these labels in the label space. So basically I have pairs, I have these couples of label xi coupled with, instance xi coupled with the label yi, with the corresponding label yi. I will denote the sample size by capital N, okay? And this is all I have about my reality, okay? So I have a finite sample representing the reality. Hopefully it is a representative. And alternative look on this is to say that I'm sampling these couples from the joint distribution pxy, again under this IID assumption. Okay, so basically I'm sampling this joint distribution space, and of course I can reduce basically this setting, the right-hand side setting, to the left-hand side setting, not vice versa. Okay. In this setting, the goal of supervised learning is, given this finite sample, to estimate the conditional distribution P label given instance, Py given x. Okay? So basically, estimating this conditional distribution is essentially estimating the map or its stochastic version between x and y, between the instance space and the label space. Once I have this map, given a new, previously unseen instance, I will be able to assign it a label. Okay? Or at least some distribution of labels. And then, for example, if I still need some definite answer, I will just take the pick of the distribution. Okay, makes sense? Is it clear? This is our goal. This is the goal of supervised learning. And arguably, it might be not appropriate to some settings, but if you have a collection of training instances with corresponding labels, this is your setting. Okay, it's called supervised learning. Okay, so what's next? Basically, what we are going to do, we would like to find, we would like to construct a map between the instance space X to the label space Y that somehow fits the finite sample that we measure, right? So the next thing is to be practical. We need somehow to go over different maps of this kind and select the best one. Okay, so we need a few more ingredients to be able to actually come up with a meaningful and a practical problem that we can solve, right? So first of all, we would like to define what is called a hypothesis class, or the space of models which we allow to use to approximate this map. Of course, we can say that any function will go, but maybe any function requires an infinite number of parameters to somehow describe, right? This is clearly not a practical problem to solve. So we would like some family, some subset of functions of this form x maps to y. Okay? And we'll call this a hypothesis class denoted by calligraphic H. Okay? For example, in the case that will be of interest in the scope of this class, obviously these will be parametric nonlinear functions that we will call neural networks. Okay? But basically, this can be any set of functions. Typically, it will be a parametric set of functions with some finite number of parameters that we can tune, and every setting of these parameters will correspond to a different map. Okay, so basically, just a trivial example. Let's say we have a linear, what is called the linear hypothesis. Let's think about the regression problem. So what we have is this function h represented as an inner product between a vector of parameters w and the input data. Plus we have some, basically it's an affine function, right? So we have some offset parameter that I'm calling as wn plus 1, okay? And I have n plus 1 parameters that I can set, okay? So for every setting of this w, I have a different map between x to y, right? It's a linear map. Okay, so essentially, let's reformulate our task. We are still trying to estimate our target function f, or the conditional distribution, but now it will be not just finding something that resembles like that map. Let's find a model within our class of models, within our class of hypotheses, that approximates f, that approximates the target function. Okay? So we would like to fit the target function from the finite sample, from the training data, but our model will be restricted to lie in this model space. Okay? So just an example, I have the instance space on the left, the label space on the right, and this is one of the possible hypotheses that maps x to y. Okay? And it corresponds to a point in the hypothesis class. Let's call it h1. For example, this class is the class of for example, linear functions or affine functions that look like this. Okay, as we've seen before. So every setting of w gives me a different point in this space, and a point in this space corresponds to a mapping like this. Okay, if I have another map, it will correspond to a different point in the hypothesis space. Okay, and maybe my target function doesn't lie in my hypothesis space at all, and this would be usually the case. It might be some function that is very complex, and my model only approximates it. There is still some error. Sorry. There is still some error between the best function I have in this space and the real target function. Okay, and again, we would like to find the best function in the hypothesis space that approximate f. Okay, so we now have a training set. We have a space of models, maybe some parametric set of models. Now we need to define what do we really mean by the best, right? So we need some criterion, some numeric criterion that quantifies how good is my hypothesis, how well it describes the training data. Okay? So the next ingredient that we are talking about is called the loss function. In different literature, it is called risk, regret, cost, objective, or basically you name it. So loss is something that we would like to minimize, as well as regret and risk. Sometimes we have score, sometimes we have reward, sometimes we have basically all other names that we would like to maximize. Okay, so in our case, we'll call it loss, and we would like to minimize this loss. So a loss will be a functional. A functional is a function of functions, right? So this functional receives our hypothesis h. It receives the true target function f, and it gives us a numerical value, a scalar, telling us how well h approximates f. Okay, quite straightforward. So so once we have this function, we can formulate supervised learning finally as something that has a mathematical rigor. We formulate this as a minimization problem, where we try to minimize this loss over the space of hypothesis h. Okay, so we are interested in the argminimum, in the minimizer of this function or of this functional over some family of functions. Okay, and I'm still not saying that this is a practical problem, but at least this problem we can study its properties, right? At least we have something tangible. Now, almost in every case, in every imaginable case, at least it is very convenient, we are going to construct that loss from pointwise loss functions. So basically, I will define lowercase l that receives y hat. Y hat is basically this. Y hat is the inferred label given an instance x. Okay, so if you have a model that you call h, you have a hypothesis. So you selected some function h. I give you an instance x, and you produce a label. Okay, this can be a label. It can be a label distribution. Basically, it works in both settings. Okay, so if you produced a label for an instance h, which I call y hat, now I can compare it to some true label y. Okay, and give you a number. This is called a pointwise loss because I'm evaluating at a single point, at a single argument of h, and not for h as a function. Okay, and of course the true label is given by applying the real target function to the same instance. Okay, so I have two labels. I need to compare between them. For example, if we have regression, let's say with a scalar valued regressor, so basically my label space is R, I can think of a quadratic loss. Okay, L2 distance between y hat and y. So I'm just penalizing as the square distance between y and y hat. Okay, yes, sure. So basically, this functional accepts h as a function, okay, a mathematical object that is a function, and gives me some quality measure of how well it fits another function f. Okay, so it's some distance between two functions. Okay, so the way I'm going to build this distance between the functions, I'm going to evaluate the distance between the functions at a given point x. Okay, and this is the pointwise loss L that I'm defining here. Okay, and then I somehow going to aggregate basically this pointwise loss into a functional L capital. Okay, so what would be a natural thing to do here? Let's take expectation over x going from the instance distribution, right? So you have some instances that happen very frequently because they have a peak in the distribution, and some instances never happen. So I don't care about how badly I approximate my label in places of the instance space where I have no density, right? So somehow I probably need to integrate with respect to the instance density. So I would take an expectation of that loss. So we'll get to that point, okay? So, but currently, if I know how to define a pointwise loss, so for example, for regression, it could be a quadratic error, a squared distance, or let's say I have a binary classification problem. So I have a class like positive and negative. Let's say I'm building I'm testing some medical condition. Let's say the guy has cancer or has no cancer. So I have two possible outcomes, and I would like to give a penalty on deviation from giving the right outcome. Okay, so we'll talk about it more in details. What is the right loss to choose? Okay, and you will see that there is no definite answer. But again, these are just two trivial examples. Yes. Yes, exactly. So this is. Oh, sorry. So it's written regression. Of course, I wanted to say classification. Thanks. Okay, so it's not regression, obviously, it's classification. It's meaningless in regression. Yes. Well, you will see that this is not in the domain of mathematics to find an optimal loss function for a problem, at least in most cases. Okay, I think you can easily argue against some optimal loss because it is very much domain and application specific. Okay. So once we have this loss function, of course, we can formulate supervised learning as an optimization problem, but how exactly do you choose the loss function? So basically, in the ideal world, it is an application specific. So let's say you have a customer that wants a learning solution for a specific problem. This customer comes with a specific business need, right? And she comes with some meaningful loss that somehow reflects that business knowledge or some other knowledge into the loss function. So this is how it works in the ideal world. In reality, of course, typically the customer will not even have the language to properly formulate anything in the form of a loss function. And then we have two typical choices. So one choice would be what could be called a plausible loss function. So a plausible loss function is something that has a certain merit that can be rigorously defined, or maybe you say that this is the right loss function to use if you agree with a certain assumption. Okay? So let's say if you agree that I have white additive Gaussian noise in my problem, then the right loss function, and I can prove it mathematically, is to use the L2 distance squared, right? What we have seen before. But then you can argue to death whether this assumption of white Gaussian noise is the right assumption or not, and probably it is not. Okay, or at least it is some kind of an oversimplification of the real world. Okay, but once you agree on that assumption, and you typically don't, then you can prove something mathematically. Okay, so this is a plausible choice. Another choice is more pragmatic. So you say, I have no idea. I have no idea what the world looks like, but this is what I know how to minimize. Okay, so I know how to minimize the L2 distance. It's easy, right? It has closed form expression, so let's use it. And I don't care whether it is right or wrong, right? Because I cannot minimize anything else anywhere. Okay, so let's just use L2 because this is what I know how to solve. And I think there is basically, there has been quite a big merit to shifting from problems, from incorrect models that we know how to solve to more correct models that we may try to solve. Okay, so deep learning is more or less all about using more complicated models that, at least on paper, we don't know how to solve, but in practice we do. Okay, so we'll talk about it when we talk about how actually to do optimization. So we'll see that these are non-convex functions that if you ask a mathematician, the mathematician will say you cannot solve them. Basically, you cannot find a minimizer of a convex of a non-convex problem. Okay, but still in practice things work. And just as an example, so let's again have a look at this binary classification example. Okay, so let me draw the famous table. So here I have y. Let's call it 0 and 1. So 1 will call it 0, will call it negative, 1 will call it positive, and this is my hypothesis 0 and 1. Okay, so the traditional names in statistics for these 4 possible outcomes. So my hypothesis tells negative, and the ground truth is negative. What is the name for this situation? It's called true negative. Okay, and this is of course called true positive, right? So if my hypothesis tells negative, but in reality it should be positive, it is called false negative, and this is called false positive. Okay, so I have 4 possible outcomes. I'm on purpose taking a trivial problem, but it is a very practical, still very practical and very common type of classification problems. So suppose now I would like to find a loss function. So remember, a pointwise loss function is a function that assigns a numerical value to this pair of ground truth label and hypothesized label. So I have basically 4 situations to define, and I need to put 4 numbers in these 4 squares, right? This is my loss function. This is how I define it. So suppose now, let's say I have a biometric system that grants access to some top security facility, okay? And basically, of course, it is only restricted to top secret employees that work in that facility. I have a zillion of other security checks before I reach to that biometric system. So let's see what would be the right way to assign numeric outcomes to these 4 squares. So let's say what is the outcome of, let's consider a false negative. Okay, so I'm Bond, James Bond. Okay, so I come to that system, and that system tells me nada, you're not. Okay, so I'll try again and again. Maybe I'll spend half an hour trying to enter. Eventually, I will enter, right? Well, so you spent half an hour of precious time of Mr. Bond. That's quite bad, right? But not terrible. What happens in the case of a false positive, on the other hand? So in the case of a false positive, some imposter is going to enter this high security facility. That's, of course, a much worse situation, right? So let's say we are putting something like 1,000 here and maybe 1 here, right? And we are not, obviously, we are not penalizing the correct answers. Okay, so this is a situation that we would have for a biometric system. Let's take another situation. Let's say we are testing some medical condition. Okay, so we have some let's say some form of cancer or some other disease, and we are giving a test to a patient, right? So let me erase this. Of course, I'm leaving the zeros on the diagonal because obviously we are not penalizing any correct answers, right? So what would be the case of a false positive? Okay, so so the guy receives an envelope, opens, you have cancer. Well, that's annoying, right? And probably the letter will say that this is only a statistical. This is only basically. This is based on some statistics, but so go to the hospital, take a biopsy, and then we'll have a definite result. The guy goes to the hospital, spends some money to the public healthcare system to take the biopsy, and the result is negative. Well, it will cost a few $100. It will, of course, be a traumatic experience, but so let's value this as 10. Okay, but what happens in the case of a false negative? So in a false negative, you are saying, well, you don't have anything, and in a few months, this guy dies because he had cancer. So we definitely would like to avoid this more. At least if you are the patient. If you are a politician, then maybe you have different choices, but at least most of us will agree that this is somehow a more appropriate way to define the loss function in this case. So you see, basically, we have two instances of binary classification problems, and we have completely different loss functions that are appropriate. One function is more appropriate to one setting, and another one is more appropriate to another setting, right? And this is not something that we could judge in the domain of mathematics. Both functions are pretty much applicable to any binary classification problem if you think of them as mathematical objects, right? So you need some domain specific knowledge or some knowledge of the value or the risk of each of these outcomes to be able to define a loss function. Okay, and this is something that only the customer, so to say, knows how to define. Okay, but basically, beyond this philosophical digression, so let's assume that somehow we obtain the loss function. So be it a loss function that the user defined, or we just invented out of the blue some loss function that we like working with. So basically, we have a pointwise loss function. How do we create that functional that tells us for a given hypothesis how well it behaves on the training set? Okay, so what we are going to do, we're going to define what is called an in-sample loss, or another name is empirical or ensemble loss. We are going to just compute the empirical mean, or the average, the sample average of this pointwise loss on our training sample. Okay? Pretty straightforward. You have 10,000 examples. You evaluate an empirical mean on those examples, and this is the loss function that you can actually compute and can actually minimize over the class of hypothesis. Okay? Make sense? And basically, this is the only thing you can compute. Or at least in the most general situation, you cannot compute anything better than that unless you know some additional information about your problem. Okay? So you don't have access to points that are not in your sample. Okay? So in this setting, let's just write what we mean by supervised learning. We would like to minimize the in-sample loss over our family of hypothesis functions. And essentially, we are going to minimize this sum, or this average over the training set of pointwise losses. Okay, again, see, you have the ith instance here. I have a black box H that I'm choosing as my model. I push the instances into this black box. I'm getting the labels. So I denoted this one as y I hat. This is the hypothesized label for the instance I. I have the true label. So this is true label for the instance I, and I compare them using my loss function that reflects my knowledge of errors of different type. Okay? And I would like to select the hypothesis H from my family of hypotheses that minimizes this objective. Okay, so let's just have a look at a very trivial example that we had before, linear regression. So I have a space of affine functions. So let me just use homogeneous coordinates. So so I have my instance x, and pardon my abuse of notation. So this is my instance x coming from my instance space, which is a subspace of Rn. I'm going to put 1 as an n plus first coordinate. And then basically an affine function looks like a linear function. Okay, so basically that constant plus wn plus 1 will be just absorbed into the vector of parameters w, which will now become n plus 1 dimensional. Okay, this is a standard trick. Basically, what is written here, let me write it as w transpose x, and again, this is actually these are the n coordinates of the instance plus wn plus 1. Okay. So basically, suppose I have a quadratic pointwise loss, not because this is the best thing for a specific problem, but just because I know how to minimize this loss, and you will see we'll get an elementary closed form expression for this problem. So I have a linear model, a quadratic loss. This sounds like a very nice combination to work with mathematically. And this is my in-sample loss. Okay, so this is my in-sample loss. Let's substitute this expression here. And I'm going to get this sum of quadratic terms, and they are quadratic in W. So remember, we would like to choose a function from this class, right? And the functions in this class are parameterized by the vector W, right? So essentially, selecting H is akin to selecting W, right? And W has n plus 1 degrees of freedom. So I'm essentially optimizing over Rn plus 1 over the space of parameters. Okay? So I will write this loss is essentially a function of W. Okay? So let's see what we have here. We have a linear expression in W squared, right? And then summed over all the instances in the training set. So I have a quadratic function of W. That's nice, right? It's an easy function. So let's just write it in a prettier way. I'm going to arrange my training instances into a matrix X. So the matrix X will be n, well, basically because I'm working with these homogeneous coordinates, it will be n plus 1 times capital N. So each column of this matrix will be an instance, okay, and we'll have n capital such instances. So this is the matrix here. And I have inner products with this matrix by the vector of parameters W, which is the same for all instances, obviously. This is just one model that has to fit them all. Okay, that's why I have this inner product. And then the vector Y. So the vector Y will be simply the corresponding n capital dimensional vector of labels corresponding to each of the instances. Okay, so in this form, I will simply have this L2 norm squared as my loss function. Okay, quite straightforward. Yes. No. So the columns of x. So x. So this is x1 sample instance 1, and this is instance n. Okay. So we are always thinking about vectors as column vectors. Okay, unless we say otherwise. Okay, so let's just do an elementary exercise in calculus. Okay, and by the way, if you need some brief reminder of how to do these kind of operations, you actually have three short write-ups on the course website. One of them is reminding you basic notions in linear algebra, what norms and inner products and eigenvalues are, things like that. Then calculus, what are derivatives, gradients, Hessians, things like that. And then another one about probability. What is a probability measure? What is a conditional expectation? Things like that. Okay? So just if you need to remove some rust, this is probably like a survivor's guide to these three topics, which we are going to use extensively in this course. Okay? So back to our problem. So we would like to minimize this quadratic expression. I'm just removing the constants for the sake of simplicity. I'm dropping this 1 over n. Let's open this norm. Okay, this is how I open this norm. See, it's a quadratic expression. Look shocked. It's okay, but please remind yourselves what an L2 norm is. Okay, so I will take the gradient of this. It's a function of W, right? It's a function of W. So I'm going to take the gradient of this. I'm saying gradient. It's a derivative. Basically it's a vector of partial derivatives of this function. So it's a convex function. Okay, it's a convex function because basically it will have a quadratic form of the form W transpose X, X transpose W, and this matrix is positive semi-definite. Okay, and hence this is a convex function. So it has one minimizer, or at least it might have an infinite number of minimizers, but they all attain the same global minimum if we have some zero eigenvalues. And basically, how do we find this minimizer? We take the gradient with respect to W and we equate it to 0. Okay, so basically we demand the gradient to be equal to 0, right? And this is a sufficient, and in case of convex functions, a sufficient, it is a necessary optimality condition. In case of convex functions, it's also a sufficient condition. And if we take the gradient, we are going to get this expression, right? Well, it's not surprising, right? So just set n, lowercase n, to be 1, in case you have just scalar functions, and you are going to get a derivative of a quadratic function. Obviously, derivative of a quadratic function is a linear function, right? Okay. So we need to solve this equation. So we have equation 0 equals to this expression, to this linear expression in W. We have a linear system of equations in W. We solve it like this, okay? And we get a solution. So in case the inverse doesn't exist, we'll do a pseudo inverse. Okay, and basically what we found is the optimal set of parameters. Optimal meaning minimizing our loss function that we chose. So now if we select H W star, H parameterized with this W star, it will be the best out of all linear hypotheses to fit our training set. Okay? Any questions? Super easy, right? Yes, question? Yes, please. Mm-hmm. Sure. So then we'll have what is called a pseudo inverse. Okay, so it will be a pseudo inverse. There are many ways to define a pseudo inverse, but basically, what you are saying that in real cases when you have many more dimensions than training samples, which is a bad situation, obviously, you have too many degrees of freedom and too little data, you are going to have zero. You're basically going to have a rank deficient XX transpose, right? So we are going to have 0 eigenvalues. And as a result, basically in those directions, you cannot invert the matrix, right? So you can define, basically you can take the eigendecomposition of this matrix and only invert the eigenvalues that are far from 0, right? And those that are 0, you will keep them 0. And what you obtain is called a pseudo inverse. Okay, so basically there is some subspace that you're removing from inversion. Another way to see what a pseudo inverse is you are basically, once this matrix is rank deficient, there are multiple solutions to this system of equations, right? So the rank deficiency is the size of the solution space, the dimension of the solution space. So what you can say, out of all possible solutions satisfying this equation exactly, you're going to, basically satisfying this equation exactly, you're going to select the one that has the shortest length. Okay, and it's easy to show that this would be again the pseudo inverse that we defined through eigendecomposition. Okay, but I'm not arguing that this is the best way to solve linear regression problems. This is just a trivial example with a linear hypothesis and a quadratic loss. So if your customer claims that, well, quadratic loss is not good because it is too sensitive to outliers, I have some error in my measurement and this can arbitrarily set off my hypothesis to a completely wrong location, well, this is an important and valid argument, and we can try putting a different loss function, but then we don't have this closed form expression anymore. Okay? Other questions? Okay, so let's move to a slightly different setting. So in the setting where we have linear binary classification instead of regression. Okay, so again, by linear, I mean that we have a class of affine functions, and again, I'm using the homogeneous coordinates for x. So basically, the offset constant, that affine part of the function, is already embodied in the n plus first dimension of w. Okay. So basically, if you think of this inner product, again, it includes the offset. It is a sign distance to a plane or a hyperplane. I have an n dimensional space. This is my instance space x. So I was not given an n-dimensional screen, so please satisfy yourself with a two-dimensional screen. So basically, this is my hyperplane that I drew here. Okay, and the vector w, or at least the first n coordinates of this vector w, define the normal to this plane. Okay, so the normal has a direction. Okay, and basically, it splits. This plane splits the space into two parts. One of the part that is on the normal side of the plane, the side that is pointed towards by the normal, we'll call them as a positive side. Okay, because the inner products will be positive there. This sign distance will be positive on that side of the plane, and on the side of the negative normal, this sign distance function will be negative. Okay. So basically, we're splitting the space into two parts. And of course, we don't really care about the distance to the plane. We only care about the sign, right? We want to split the space into two parts. One of them is going to be positive, another one is going to be negative, because these are the two labels that we know how to assign, right? We have a binary classification problem. So we have two labels, and by this convention, we are calling them +1 and -1, or if you will, it can be 0 and 1, okay? That's why we are putting this sign function. Okay, makes sense? So we transform a linear regressor to a linear classifier by putting this sign function on the inner product. So it is funny that this function is not linear in W anymore because of the sign, right? Actually, it is a very nasty function. It's not even smooth. Not talking about being differentiable, so it's not even continuous. Okay, so it has a discontinuity at 0. It's pretty bad. Okay. So we could naively remove the sign function and just continue solving the problem as we did in the case of linear regression, right? Okay, but in any real world situation, what happens is that you will have some false positives and false negatives, right? And at least in this setting of binary classification, it doesn't really matter how distant is your instance from the decision boundary, which is this hyperplane. You would like to treat it more or less equally, right? So if let's say if you have a negative here, you would like to penalize it the same way as a negative here. But the quadratic loss doesn't realize this, doesn't achieve this goal. It will give a much higher penalty to this example rather than to this example. Okay, So it's probably not good for any practical purpose when you have even a small amount of outliers. You want something that doesn't penalize quadratically, something that saturates very fast to some constant, right? So it's not good to solve binary classification problems as regression problems. Okay, so let's do a break, and after the break, we'll see another instance of a problem that is called logistic regression, which, despite the name, is actually a binary classification problem. Okay, let's continue. So I hope until now it was more or less trivial, right? We haven't seen anything beyond elementary algebra and multivariate calculus and some probability. So things will get slightly more sophisticated down the road, but again, this is not a theoretical class. So let's move. We basically just convinced ourselves that solving binary classification using basically the same formulation as we had for regression is a bad idea. So let's see another setting that is very frequently used for binary classification that is known under the name of logistic regression. But again, despite what the name suggests, this is actually a classification problem. Okay. So basically, what we are going to do, we are going to model the target distribution. So the target distribution is this conditional probability of label given the data. Okay, and in the case of a binary classification problem, we have just two possible values here. It can be y equals 0 or y equals 1, right? And given the instance, obviously the instance is some continuous vector in some high dimensional space. Okay, so the way I'm going to model my target distribution is going to be this. I have this inner product with x. Okay, and again, I'm thinking of x in homogeneous coordinates, so there is also an offset and a affine part of this function. So I'm going to measure this sign distance from the plane, right, that the normal W defines. And then I'm going to plug it into this function 1 over 1 plus exponent of that result. Okay, and what is particular about this function? So the exponential, of course, goes from 0 to infinity, right? When it is 0, this function gives me the value of 1. And when it is infinity, it gives me the value of 0, right? So basically, no matter what x I plug in, the result will always be between 0 and 1. Okay? So it's nice, because I'm expecting probability, right? Probability has to be between 0 and 1. And obviously, the counterpart for y equals 0, this is actually 1 minus this expression, right? So if I do the math, I will get this exponential in the numerator. Okay? So this will be my general form for the target distribution. And this is what so I would like to estimate the target distribution. I'm estimating it in this parametric form. Okay? So essentially, instead of estimating a probability measure, I'm estimating the set of parameters W. Okay? So, and here we have a bug in the slide. So at inference time, I'm going to assign the label y equals 1 if, so you tell me if, what, so I have two probabilities. So I'm given the data x, I have the probability of label being 1 and the probability of label being 0. So if this probability is bigger, right, I'm going to assign label 1. If this probability is bigger, I'm going to assign label 0. Okay? It's called maximum likelihood, right? So I'm going to just check this ratio, and this ratio, very simply, is just this exponential. The exponential of the inner product of the sign distance to the plane that we had. Okay? So if this exponential is bigger than 1, I'm going to assign label 1. If it's smaller than 1, I'm going to assign label 0, which is obviously it happens if and only if the sign distance to the plane is bigger than 0. Okay, if I'm on the positive side of the plane. Makes sense, right? So I'm just doing exactly the same thing that I was doing, but no sine functions, right? There is no sine function. So you can think of this. This is called the logistic regression function or the softmax function. We'll find it under the sigmoid function. So basically, this kind of a smooth function that goes smoothly and basically continuously differentiable from 0 to 1, you can think of it as some kind of a relaxed sine function. Well, sine function would be also scaled by a factor of 2 minus 1, something like that, right? But basically, it has the same effect. So I don't have anything discontinuous here, okay? And of course, otherwise we'll set y equals 0. So this is our model. And we would like to maximize the likelihood of the training labels given corresponding training instances. Okay, so I know what is the label that I'm supposed to get from each instance xi. It's the yi that I was given in the training set. I will plug in my xi into my model, and we'll see what is the probability of being y equals 1, right? So basically, this is the function that I would like to optimize. This is the product of point-wise probabilities, p, y, I given xi. Okay? Of course, this is actually a function of w, right? Remember that conditional probability was a function of w. W is my set of parameters. For every choice of w, I have a different probability distribution from that parametric family of probability distributions. Okay, so I would like to fine-tune my w in such a way that this value is maximized, that my model maximizes the likelihood over my my finite sample of training data. Okay, so I'm assuming that, of course, this by writing this product, I'm making assumption that my sampling was done IID. I'm assuming independence. Okay, and so independence means that I can write this joint distribution as a product of individual distributions, and so this is the independent part, and the identically distributed part means that it's the same function for every instance. Okay, and if it's not, well, it's not exactly the situation I would like to be, even if it's true. Okay, so I will assume that I have IID sample. So I will take a negative log function. Okay, so basically maximizing this product is equivalent to minimizing, so that it has the same minimizer as minimizing the sum of the negative log probability distributions, right? Minus log basically turns maximization into minimization, right? And it's actually nice to work with a negative log because basically if I plug in the exact expression that I had before for this probability, actually for its negative log, I'm going to have, so I'm just writing it this way. I'm using the fact that yi can be either 0 or 1. Okay, so you see, by the way, we are freely switching from y being plus or minus 1 and y being 0 or 1. That doesn't really matter, right? These are just two conventional names that we are giving to our labels in binary classification. So in this case, it is more convenient to work with 0 and 1. So I'm using the fact that y can be either 0 or 1 to write it this way. So basically, all the instances in which y equals 1, basically this term, the first term, will be alive, and I have this conditional distribution. And all the instances where y equals, so here yi equals 1, basically this term will be alive. And if yi equals 0, it will vanish, right? And this term, the other way around, whenever yi equals 0, this term will stay, okay? And otherwise, it will vanish, right? And basically, if you just do the math, you will see that plugging in this expression for the case of yi equals 1, y equals 0, you will basically get this expression that I wrote here. I think it's correct. Check my math, okay? So if it's wrong, then Let me see. But hard to do it in real time. Yeah, of course. So obviously, this is just a product. Okay. Obviously, basically there are two cases, right? Y equals 1, y equals 0. So I will fix this bug in the slides. So basically, it's when you have y equals 1, you have this conditional probability for y equals 1, and this basically this is the complementary case. Okay, so you have two terms. So now let's plug in the log. So what we have is basically we have this expression for basically for whatever remains from the exponential, and this log of this expression is what remains from the denominator. Okay. So if you do the algebra, you get this expression. It's quite straightforward. Basically, this is the loss we would like to minimize with respect to the parameter w, right? So basically, it's a function of w. We would like to find the target distribution, which is the conditional distribution of label given the data. And in our case, we modeled it as a parametric distribution, so we just need to find the optimal parameters. Okay, so we want to minimize this. We would like to minimize this loss. Okay. So here it will be just the sum of these terms, and of course, here it's xi. Okay, so I would like to solve this problem, minimize this objective function to get the optimal parameters of my classifier, right? And this classifier gives me the probability of being in the positive class and the complementary probability of being in the negative class. What it turns to be a convex optimization problem. So you see, you have a linear expression here, which is easy, and you have some log of 1 plus exponent of w transpose xi, and this turns to be a convex function. Obviously, a linear function is also a convex function. So a convex function means that we can find a global minimizer for this problem in polynomial time. There are efficient algorithms that can solve minimization problems with convex objective functions. So essentially, this problem is solvable. You see, we overcame by using this smooth logistic function. We overcame the problem of having a discontinuous sign function. Okay, so we did binary classification without suffering from any lack of continuity or lack of differentiability of the sign function. Okay, and we actually have a global solution for this problem. So we had a closed form solution, obviously a global minimizer as well for the for the quadratic regression problem, and now for the logistic regression, which is a classification problem, we also have no more a closed form solution, but a global solution that we can find numerically very efficiently. Okay, so this is of course a very nice situation. These are TOE examples. It would be very cool if linear models could do the job very well, but let me just give you an example of a function that of a classification problem that is not solvable by linear hypothesis. Let's suppose I have n equals 2. Okay, so this is x1, this is x2, this is my instance space. Okay, and my function, suppose it gives me, so I have a sample that gives me -1 here, -1 here, +1 here, and +1 here. So think of a XOR function. Okay. So I bet you cannot find any hyperplane that can split these points without making a mistake, either of the first kind or the second kind, without producing false positives and false negatives. Okay. So these points are not linearly separable. There is no way to find a hyperplane that can perfectly classify them. And this is a very simple example. So imagine how poor in terms of representation capacity are linear classifiers for real-world problems. Okay, so of course you will find in the real world you will find many non-linearly separable types of data. Okay, Therefore, we need to do something better. Of course, we know how to solve linear classification and linear regression problems, but linear models might be simply not enough. And I think there was basically a lot of merit from going from linear models that we know how to solve to nonlinear models that we might attempt to solve. Okay, so let's think about two possible ways of doing it. So two possible ways. One of them, okay, so you say your data are not separable in their original instance space. Let's do a trick that sometimes is called lifting. So let's map our original instance space into something very, very high dimensional, some very crazy space. Let's call it a feature space. So we have some nonlinear map phi. And let's hope that in that high dimensional space, the data will become linearly separable. Okay? And then we'll use a linear model to separate it. So again, you do a nonlinear map, and then you do linear classification. Okay. One more interesting thing is that what is written here is essentially an inner product between W and phi x, right? So if you do your algebra carefully, you will see that you actually don't need the phi itself. You just need an inner product with the phi. Okay, an inner product in that high-dimensional feature space. So if you know how to define this inner product in the form of what is called a kernel function, you don't actually need to build this phi. And this phi can be infinitely dimensional. Like a Gaussian kernel, for example, can only be realized by an infinitely dimensional feature space. Still, basically what you have here, you might basically get linear separability in that lifted space, in that feature space. What you gain is that you are still using a linear model. So models like, for example, support vector machines, like kernel SVM, support vector machines that use this kernel trick, lift the original instance space into some high-dimensional feature space and then solve a linear classification problem. Okay, so the SVM problem, you will see it in the first assignment, is slightly more clever than what we did with logistic regression and quadratic regression problem, but essentially it's the same. It uses a linear model. Okay, in the new space, linear model has more power than the original instance space. But still, the map phi is fixed. You don't learn it. So basically, you need somehow to get the knowledge which kernel or which map phi gives you good features. So you need somehow to handcraft your features. And of course, there are different ways of learning these kernels, but these are all ugly and difficult optimization problems. Okay. And today we use, basically, when we speak about handcrafted features, it's almost in some pejorative, some derogatory form of speaking, right? So handcrafted features. So the idea of one of the main points of deep learning, you can argue that everything that we do in deep learning today is just a rebranding of what people have been doing in the 80s with neural networks. I will argue against this point of view. There are many interesting new things that can be done. But at least in the regime of supervised learning, this might be true to some extent. What is different is the use of these models that we are applying. And the idea of deep learning that you actually learn features from the data. So you learn the representation. You don't rely on any handcrafted features. And the outcome is really spectacular. It looks like when you have enough data and sufficiently good labels, you can actually learn better features than any brightest mind can handcraft. Okay, so this is one of the hallmarks of deep learning, at least in the supervised regime. And we'll see other regimes where it also has a lot of merit. So basically, the alternative that deep learning offers is essentially not to handcraft features, but actually to use a nonlinear model. Okay, and by nonlinear, I mean that the dependence on the vector of parameters W is nonlinear. Before, we had a linear dependence on W. We had some very crazy feature map, but that was fixed. That was not part of our optimization. The classifier before was a linear function. Now it is not. Okay, this alternative that deep learning advocates essentially is to use a nonlinear model. And our nonlinear models, extremely nonlinear models, will be deep neural networks that we will see next week. Okay, so essentially by optimizing over the parameters of the neural network, you will obtain some feature space. So some intermediate outputs of the network could be thought of as a representation space. Okay, and we'll actually use it explicitly when we talk about generative models. So essentially, you learn your features from data in the way that minimizes the loss, that optimizes the task end to end. And this is something that we didn't have in this older approach of handcrafting the features. Obviously, nonlinear models are harder to train, but we will see that there is some magic that still it works. Okay. So just as a visualization, in the first case that I described, we go from the instance space to a feature space by some fixed nonlinear transformation, that is this curled arrow, and then we use a linear model H from the feature space to the label space. And hopefully the feature space is richer, so the linear model performs better. Okay? In the deep learning approach, the model is directly nonlinear. So we are looking for nonlinear maps from the instance space to the label space. Okay? And of course, we will need to define the family of these hypotheses, these nonlinear models, and learn how to optimize them. Okay? So this is something we are going to see in the next few lectures. Now let's try to answer the following question that I'm sure bothers you from the beginning, right? So what we did, we minimized the in-sample loss, right? We defined the loss on a finite sample that we obtained from the joint distribution or from the marginal distribution of the instances plus the labels that we got by applying the target function, right? So why on earth this is going to be useful for any instances that we have never observed during training? Is this obvious that it will be useful? Well, let me show an example. So so it depends a lot on the hypothesis class, right? So I can construct a very rich hypothesis class, let's say that looks like a table, okay, a lookup table, into which I'm going to put all my training set. Okay, so whenever I encounter an instance that looks exactly like the instance in my training set, I'm going to return you the label that I memorized. Okay, so what will be the value of the in-sample loss that let's say in the case of the L2 loss, it will be strictly 0, right? So I'm going to do perfect job on my training set. Okay, and then comes the inference time. So at inference time, I am facing a previously unseen instance, and I would like to give it a label. Will this lookup table give anything meaningful? No, right? So let's see just a visualization. In the case of regression, so I have my so basically the white curve is my latent target function. I don't know it. I can only observe it through these sampled points. Okay. So what I'm plotting here in orange is a hypothesis. It does perfect job on the training set. It exactly fits the data. Okay. But it's not. It doesn't. It overfits the data. So I'm getting excellent performance in terms of the in-sample loss, but I would say that you will all agree that it is completely useless outside the training set. Okay, so very wild things can happen outside those samples. So this is called overfitting in the machine learning literature, and the question is, why learning works? Why don't we overfit all the time? Okay, so let's try to answer this question. So I'm not going to answer this question with full detail, but at least give you some hint why it might work. So let's distinguish between two types of loss functions. So basically what we had was the empirical loss, right? The in-sample loss, the loss that we can compute on the training set, right? We have this n, which is the training set size. We had the set of pairs xi, yi, right? This was our training set. And we computed the empirical mean, the average on the training set, of pointwise losses that we denoted by L. Okay? Now, what we would actually like to evaluate is what is called the out-of-sample loss or the generalization error. We would like actually to compute the expectation of the pointwise loss on the joint distribution xy, right? So you really want to compute an expectation, but you don't have access to the distribution. You only have access to a finite sample from the distribution. So you approximate the expectation by an empirical mean rather than a real mean. Okay. So basically, this is a statistic. So think of it as some kind of crazy nonlinear moment of this probability measure. Okay, and you would really like to compute the real moment and not a statistic, not a finite sample estimation of that moment. Okay, or in terms of the target function, you can think of this expectation taken on the marginal distribution, on the instance distribution, with the target function appearing in the loss. Okay. So this out-of-sample loss, this generalization error, is what you would like to minimize. But what you minimize in practice is the in-sample loss. Okay? Of course, the generalization error cannot be computed unless you have the knowledge of the distribution. If you have the knowledge of the distribution, then basically you can do a lot of things. But this is not practical. So basically what we have is a gap. You have some difference between the in-sample loss and the out-of-sample loss. And you would like to say something useful about this gap, right? If you cannot say anything useful about this gap, you cannot guarantee that learning will work. Okay? Because basically, this term tells you how well you generalize. It tells you how you perform on all instances in the average, in the mean, right? But what you really minimize is this. So unless you can tell that minimizing the in-sample loss will also do something good, will also somehow decrease the out-of-sample loss, there is basically no guarantee that learning will be useful for anything. Okay? So just to note, this and these are completely different mathematical objects, right? So the out-of-sample loss is an expected value of some function of our random variables, right? It's a deterministic quantity. It's a scalar. What about the in-sample loss? It's a random variable, right? Every sample from the training set will give you a different realization of this random variable, okay? So let's assume again that we are drawing our training set IID from our joint distribution, okay? So basically what you have in our in-sample loss is a sum of statistically independent random variables. Okay? So basically each of these variables is drawn independently from the correspondingly transformed from the correspondingly transformed probability distribution, right? So we have a sum of independent variables. What will happen if we evaluate its mean, its first order moment? So let's take the expectation of this function. So we have the expectation of the in-sample loss is essentially the sum of the expectations of these pointwise losses, right? Expectation is a linear function. And, well, you're going to get simply this, right? Which is nothing but the out-of-sample loss. Okay? So basically, every term here has the same expectation as the out-of-sample loss that you would like to estimate, right? But you don't have access to. Okay, question? Yes. No, of course. I'm not saying that I know why deep learning works, right? But at least in this setting, we're not talking about deep learning. This is basically any supervised machine learning needs to answer this question, right? So of course, I'm making IID assumptions. We'll see that basically independence will be playing a bad joke. We need some more delicate analysis. But basically, you see that each of these pointwise losses is a random variable that has the same mean as the out-of-sample loss. Okay. Now, what you have is a sum of a big number of independent random variables drawn from the same distribution because of this IID assumption that has the same mean as what we would actually like to work with. What can you tell about the behavior of this random variable, about the sum of these independent variables, or the normalized sum, the mean, the empirical mean? Okay. What else? Even more important, not the shape of the distribution, but what happens to the variance? Exactly. So basically, this is what is called, or at least one of the forms of what is called the law of large numbers. It tells us that essentially this in-sample loss will concentrate about its mean, and its mean exactly the out-of-sample loss. Okay, so basically, it will go from something like this for a small sample to something like this for a bigger sample, and it will converge to a delta when the sample becomes infinite. Okay, so it will concentrate about its mean. Now, what we can then do, we can draw this distribution, put some tolerance epsilon around the mean, and ask what we can tell about the probability in the tails. Okay, so basically, I'm going to take this generalization gap. Okay, and I will ask what can I tell about the probability of this. So the generalization gap is what is drawn on this axis, or basically this is L in, right? But gap will be basically the difference, how much I deviate from this mean, right? It can be either positive or negative. I don't really care about the sign. I just care about the magnitude, and I will ask what is the probability of being bigger than epsilon. So basically, what is the probability of being in the tails here? Okay, and hopefully I will get something. I will get something that that decays fast, right? So I want something, let's say something exponential, right? Something exponential that probably improves as my sample size grows, right? So this probability of something bad happening, right? Of being in the tail, it's bad. I would like to not to be in the tail. I would like to be around the mean. So I would like something. So it will be negative exponential, right? We'll have something that depends on n probably, right? That if I increase the sample size, this probability drops, and probably something that also depends on epsilon, right? Okay. So this what I'm writing here is the sort of tail bounds that I can derive, at least in this IID setting that we have put forth. So basically, we can write what is called the Hovding inequality. You see, it is basically, it looks very similar to what I wrote before. The advantage of what is written here that it is correct. Okay, but essentially it behaves in the same way. So I depend on the sample size. I depend on the tolerance. You can see that the dependence on the tolerance here is quadratic. Okay. But basically, what essentially we did, we wanted to state something like the in-sample loss equals to the out-of-sample loss, right? So we minimized one quantity that we could compute, and consequently, we also minimized another quantity that we actually wanted but couldn't compute, right? But there is no way I can claim anything like that. So this identity is simply wrong. But now what I'm saying, I'm allowing two relaxations of this statement. So one relaxation is to allow this identity to hold approximately, okay? And another relaxation, I'm allowing this identity to hold with high probability, but not always, okay? And basically, it's so conceptually, many things become possible when you put them into these settings. So something that you cannot say about being always exactly true becomes true when it is probably approximately correct. Okay, so basically we have this statement, this tail bound, essentially is essentially equivalent to saying that the in-sample loss equals to the out-of-sample loss. Probably that this statement is probably approximately correct. Okay, so essentially we have this tolerance constant epsilon and the certainty with this basically this probability bound, or we can call it uncertainty actually, or 1 minus this quantity can be called the uncertainty. So this is, so 1 minus this 2 times the exponential is the probability of not satisfying the the identity approximately. So basically the tolerance is responsible for the approximately, and the certainty is responsible for the probably in the probably approximately correct setting. Okay, and you see that we have a quadratic dependence on epsilon. So if we would like to decrease the tolerance tenfold, so basically we would like to be more strict about this, the exactness of the of this equality, we need to increase the sample size by 2 orders of magnitude. Okay, which is still might be very impractical if you actually develop these bounds. Okay. Now pay attention that what we wrote was for a given hypothesis H. Okay, so basically it was good for testing how well a given hypothesis generalizes. Okay, so I'm giving you H, and you tell me that this H is probably approximately correct because it achieves a certain tolerance epsilon with very high certainty. Okay, but learning is not about verifying the quality of a single hypothesis. It is about actually going over a pile of different functions H and selecting the best one. Okay, so if we now make this pile big enough, you might find very bad hypotheses there that don't satisfy the inequality with good constants. So I can, for example, ask you to draw a coin from your pockets, each one of you, and toss it 5 times. Okay, and I can with high certainty tell you that one of you will have the coin falling on the same side 5 times. Okay, so this is very improbable when repeated once, but when I need to repeat it multiple times, it will happen with very high probability. Okay, so the same happens in the hypothesis space. So I really want to say something about all the hypotheses, right? Or actually the best one of the hypotheses. So basically I'm minimizing over this space H, right? So what I would like to bound, I would like to put a bound on this quantity, right? On the best hypothesis. And I would like to write it in terms of a bound on any hypothesis, right? So of course here I will show you something very naive. This will be the probability of the supremum or the maximum gap over all possible hypotheses, right? Being bigger than epsilon. So if the biggest gap, if I can bound the probability of the biggest gap being bigger than epsilon by something useful, then any other gap will be only better, right? And that other gap will be, one of them will be realized by the best hypothesis, right? That minimizes the in-sample loss. Of course, this is very naive, but we can try going this direction. So basically, here I have the probability of this supremum over all the space of hypotheses, and I can write this. So basically, it's just a union of all possible hypotheses in the class, right? Of all possible generalization gaps for all H's in my class. Okay? And then I can upper bound this by the sum of probabilities, right? So this actually will hold with identity if these sets are disjoint, right? But if the sets are not disjoint, and disjoint set means independent events, if the sets are not disjoint, it means that there is statistical dependence between the events. Of course, this will just be a bound. Okay, it will not hold with identity. A question? Yes. Again, I'm saying I'm developing it for the worst case, right? No, it can be equal if all my hypotheses produce independent events, right? Otherwise, it will be a strict inequality. If I have some non-zero probability in the overlap, in the intersection, then it will be a strict inequality. Sure, that's why I'm writing a weak inequality, because it can be satisfied with an identity. Because probability measure is subadditive, it cannot be another inequality sign. It cannot be bigger than. This is basically, this term is an upper bound, right? Okay. Now, because I'm summing over all the hypotheses in H, let's just replace this by the cardinality, the size of H, times the Hovding inequality. Basically, this now falls under what we can analyze using the Hovding inequality, the tail inequality that we had before, right? We have a fixed hypothesis H, and we can quantify the certainty of this generalization gap, right? Of course, it is a very bad idea to have the cardinality of H in the bound, because once you go to even a trivial hypothesis class of linear classifiers, which is infinitely, basically it has infinite cardinality. It has the cardinality of a continuum, right? This bound is useless. This bound is useless. So it's only useful for a hypothesis class with a finite number of elements, finite number of hypotheses. Obviously, the bad thing happened because we treated each such event, basically for every hypothesis, let's say H1 and H2, we treated each of such events as independent, right? But in reality, they could have overlaps. Okay, so basically, let's say this is one. So each of these colored sets is one of these events. Let's say corresponding to H1, H2, and H3. Okay, and you have some overlap, some dependence between the events, and somehow you would like to say that if you have two hypotheses, let's say H2 and H3, that are very close in some sense in the space of hypotheses, they should be very much dependent, right? So you shouldn't be discarding that overlap as in the naive bound that we developed. Okay, you somehow should be counting that high dependence in, and when you have a big distance between the hypotheses, well, the events should be more independent, right? So basically, you need more delicate analysis in order to obtain better generalization bounds, right? So what we did was very naive. Obviously, you need some kind of a different way to quantify the complexity of a hypothesis class rather than just counting how many hypotheses can be found there. Okay, something that would be finite for a set of infinite cardinality. And there are tools to do this more delicate analysis, like the VC dimension, the Rademacher complexity. Basically, there are analytical tools that allow you to express the complexity of a hypothesis class in a more delicate way, and then you get more useful generalization bounds. The problem is that, at least as the state of affairs stands as of today, none of these tools was found useful in the case of deep neural networks. Okay, so basically, all the bounds that you can get with tools like VC dimension or the Rademacher complexity or other tools are too loose to be useful. Okay, so that's why I don't even bother to define you what VC dimension is. It is a useful tool, but not in the case of deep learning. So somehow we need probably, in view of many empirical results that we know and some pieces of theory, somehow we need to develop new tools or to completely rethink what we mean by generalization, because at least the existing tools do not really manifest themselves as useful in the case of attempts to analyze deep neural networks. Okay, but still, even though we cannot tell much about whether we are going to generalize well or not, we have quite good practical guidelines how to make sure that our model that we are training in the supervised regime will do a good generalization. Okay, so we'll see this kind of art and little science, mostly art and little science, in the subsequent lecture and subsequent tutorials. Basically, how to make a deep learning scenario work. Okay, so basically, we just need to admit that we don't really understand why it works. Okay, so it's a little bit scary, and some people will protest, and many people do not want to use deep learning exactly on these grounds, but still, it is undeniable that these models give excellent, spectacular results in many settings. Okay, any questions? Of course, of course. So let me just elaborate again, make the statement more precise. So, of course, you can compute the VC dimension of a neural network. It will be some finite number, some big finite number. When you try to use it in these kind of bounds that we showed for generalization error, you will see that these bounds do not describe the real behavior that we actually observe in experiments when using neural networks. So, for example, you can see how neural networks can perfectly fit completely random labels. Okay, so basically there are a few phenomena that we observe in practice that are not exactly explained by these bounds. So these bounds are useless. They are not tight enough to give anything useful for the actual practice with deep neural networks. I'm not saying that you cannot compute the VC dimension of a neural network. I'm saying that this quantity, or the bound that will result from that quantity using the VC dimension theory, will be of any practical use. Okay, so you can do that, but it will be just a mathematical exercise. Unlike many other types of models where, like SVM, for example, where this is actually a practical and useful tool. Okay, any other questions, comments? Okay, so we'll see each other next week, I guess. We'll start talking about deep neural networks. We'll talk about backpropagation and CNN. Then we are going to talk about stochastic optimization, gradient descent, some basically techniques for doing regularization of these optimization problems, and then we'll switch to more interesting training regimes like unsupervised learning, reinforcement learning, and so on.